In this unit, we're going to talk about forces. We'll start with forces in two-dimensional space, and we'll introduce some ideas that will be helpful for looking at forces in general three-dimensional space as well. Some definitions that are important. We use vectors to represent forces because, like forces, vectors have both magnitude and direction. When we're dealing with a force, the direction really is defined by two separate things. So if we have a force here indicated by the red arrow, there's two things that define the direction. One is the line of action. So the dotted line is the line of action, and we can define that by the angle that it makes with the horizontal, in this case, the angle theta. And then the sense is just the direction of the arrow. So those two things define the direction of the force, and then the magnitude of the force, and it's important to use units of force, in this case kilonewtons. 240 kilonewtons is the magnitude of that force. We'll see that it's useful to work in terms of the components of forces, and in doing that we need to use a reference coordinate system. In two dimensions, we usually use x horizontal and y vertical as our reference coordinate system, and it's useful to define two unit vectors, vectors of unit magnitude, I hat in the x direction and j hat in the y direction. After defining these unit vectors, we can express a force in what we call its Cartesian vector form. So if we have a force of magnitude f here, it makes an angle theta x with the x-axis and an angle theta y. Its line of action makes an angle theta y with the y-axis. We can define a scalar component in the x direction. We'll call that f sub x. And that's just the total magnitude of f times the cosine of the angle that the line of action makes with the x-axis theta x. Similarly, we can define a scalar component in the y direction. That's the total magnitude of f times the cosine that the angle makes with the y-axis theta y. Or conversely, the magnitude of f times the sine of the angle theta x. Either way, in two dimensions. The magnitude of the force F, again, if we have the components, it's just the magnitude is just the square root of the sum of the squares of the individual components. Also, the direction of the line of axis, the line of action of f, tangent of theta x is just equal to the opposite fy over the adjacent f sub x. Some ideas that are useful, be actually more useful in dealing with vectors in three-dimensional space, we can identify in two-dimensional space, and that's the idea of what we call the direction cosines of the line of action of a force. So the direction cosines of our force F here, we define those as lambda x and lambda y, and that's just the cosine of theta x is lambda x, and the cosine of theta y is lambda y. After defining the direction cosines, again, lambda x is the cosine of theta x, and the direction cosine lambda y is the cosine of the angle that the line of action of f makes with the y-axis lambda y. We can express our force F as its total magnitude times a unit vector, in the direction of f, and that unit vector is defined as lambda. And lambda is just the direction cosines times the unit vectors in the individual coordinate directions I and j. And this idea of a unit vector in the direction of the force F is really much more useful when we're dealing with forces in three-dimensional space.